Okay, everybody, welcome to the end of week 5. We are in session 10. We're talking fine-tuning LLMs today, and we are really, really pumped to be able to see just incredible progress happening on the build, ship, share front around the cohort, not just around the community. So I want to shout out a couple people here. First of all, shout out to Deep T. Check out this epic blog that she wrote. Look at his table of contents, okay? Incredible work. I can't wait to see more ships and more shares from Deep T. This is a first share. Okay, this is a first build ship share. So way to go, Deep T. Now, what happens when you take it to the next level a little bit? When you're doing it for a while, well, then you start to get into a place like Ben, who has been working on this slowly but surely. He's been coming to the build ship share meetups on Mondays. He's been shipping. He's been sharing. He's starting to get people reaching out to him on LinkedIn. People he's making sweet connections with. And like, man, Ben, I've been seeing your stuff. I think it's so cool. We should talk about how cool it is and talk about things that we can maybe do together. I also want to give a special shout out to Ashwin, aka Angres, on Discord. This is the guy that's kind of just been shipping, putting it out there, sharing each of his homework assignments on LinkedIn, on Twitter, every time. Just even if it's ugly, copy paste, boom, done. And then he goes out and he puts it on Reddit. And, look at this. He's getting thousands of views in the LangChain Reddit from his post on talking about RAG eval and the stuff we've been talking about in this class. This is literally taking the homework, putting it out there. Your network is more powerful than you think. And I want to end here today with this is a guy that's actually not in the cohort, but Nikolai, you may have seen Nikolai on Discord. He's in Amplify every week. He's building, shipping, and sharing pods every week. He's been doing this for a long time now. And most of the time just goes and, the pod goes and so it goes. Yesterday, he made a post and go amplify Nikolai because this is the kind of thing that you get when you build, ship, and share every single week for long enough. You hit some gold, you hit some veins of real value, and you hit some resonance in the network. And so, it's really, really amazing to see folks at different levels of build, shipping, and sharing, and people just getting started. There's all the time in the world to get started today. So, join us in the lounge every Monday. You know where? Every Monday morning. So we've got some homework also that you guys continue to really crush. Lots of submissions coming in, lots of hundreds. Arthi, what did you see on the homework when you graded homework number 6 on multi-agents?
Great submission, Greg. Overall, all of them demonstrated that they understood the concepts. Many of them attempted the bonus activity, which was great. Most importantly, a lot of very thoughtful follow-up questions that sort of reinforced the understanding. It was very nice to see those questions. And the presentations were also good. There were a few which were missing audio, very few above 5 minutes, but overall, awesome. Great going.
Love it, love it, love it. Thanks, Arthi. Yeah, we got some great lessons. Same stuff we pointed out before. We're going to get kind of back on this track. Shout out to all the shares in Discord. You guys are doing a great job. Keep it up. And shout out to the public shares. You're probably not surprised to see. Look at this. It's Ben and it's Ashwin. Oh my gosh, I can't believe it. That must be a coincidence. And then we have Deep T. Look at that. Let's go. And Lewis waiting for some bigger shares, my man. Here's the thing. We got next week coming up, and it's the perfect time to really start curating your own stuff that you're interested in coming off of your profile. Also coming up, we've got Vincent's Deep Dives next week. For those of you that don't have a big data science background, you might want to definitely join Vincent's Deep Dives next week. Today is going to be an absolute whirlwind and quite painful for some of you that have no data science background whatsoever. This is more and more the fine-tuning of an LLM becoming prerequisite material for a class like this, and something that we're likely going to consider the LLM fine-tuning, actually cutting out of cohort 6 so we can go deeper on more advanced material and kind of moving it to the front. So you guys will kind of feel that vibe today. Also, next week, you can join us to talk chains of thought in latent space. There's some adjacent papers that have been coming out too. I'm quite excited to jump in on that. Obviously, you guys provided feedback as well. I want to go around. Loved the dive into coding. They love it when you go slower, Wiz. Hopefully, we'll see more of that today. The midterm submission being chained to the final demo day. I think this is going to be a game changer for a lot of you guys. Really important for us to refine our models. Yeah, more and more, I think this is going to be true. And, I think while it was a low-hanging fruit topic, it is something that adds real business value immediately. Also, we got some suggestions coming in. Hungry for more advanced code? Well, we got it for you today. I like the code left blank, more distilling. It was really dense. If that is how you felt about the last class, just a pre-warning, the one-on-one support room is always available if you want to just go chill. And, today, again, is going to be kind of rough because we're going to really take you all the way out to the edge. But the reason is that you already know enough to get those AI engineering jobs, to do the important work with RAG, with agents, with fine-tuning the embeddings. And this fine-tuning of the chat model stuff is almost like maybe a maybe finishing step that is often, really kind of outside the bounds of many of the prototypes that you're going to be building. This, again, might be something that we see kind of have a reemergence, but today in 2025, it's really not something that I would be too worried about if I'm trying to find a job or create a startup. And some suggestions, more on midterm expectations and deliverables. Got that coming at you later in the sesh. Would be nice to see how to use unstructured.io. Again, you already know enough. You can go pick up unstructured.io today and dig in. In fact, you can get on our YouTube channel and check out where we've taken a look at complex PDFs. This is just not something that we feel like exactly fits within the curriculum, the core curriculum. And it's one of those tools that is kind of for self-study. We've got some resources on YouTube on complex PDFs to check this out. But there's an emerging space here, and you really want to, again, and this was what the midterm will push you to do, refine your use case. If you want to go grab a tool and just pick up a tool and use the tool, that's fine. You can go do that today, especially with tools like Cursor and other things. But it's like, what are your documents? What are you trying to get out of them? Do you need an unstructured? Do you need a vision language model? Do you need something else? Why? Who needs this, right? You need to start asking these questions to really be able to dig into the right tools, techniques, and best practices out here at the edge. So this is I wanted to put this in totality, maybe a single code block after the function definition, so I don't use so many OpenAI calls. This was a good idea. We're gonna actually try to implement this. Thank you for this idea. That was cool. So I think that's something we can definitely do. Easy fix. The notebooks seem too long to cover in one breakout session. I want to stress this very strongly today. You are not supposed to finish the homework in the breakout session. If you do, that's super dope. It's called homework, right? And so we want you guys to go spend some time thinking through, grokking the concepts. This is not supposed to be something where and what you'll notice is if you go and somebody gives you a blank sheet of paper, you actually can't do any of this. It's easy to click run in the notebooks, as you guys that want more blank code have continued to remind us and will continue to remind us. But it's not supposed to be done within the session. If you're doing it and crushing it in the session, that's dope. But especially today, please do not expect this, especially if you want good results doing fine-tuning. And that's another reason why fine-tuning is just not super important today, because it costs a lot of compute. And there are just other things that don't. And we are leveraging those quite a bit while we're taking stuff off the shelf. Worst breakout session ever. Man, sucks. Wasn't teaching us any particular concept, so seemed kind of useless. I would say, like, what do you mean by concept exactly? Do you mean a concept that this is useful in business, or do you mean a concept like we need a specifically new type of coding, architecture, or pattern to look at? Because I would say, like, as mentioned in some of the previous feedback, some of the lowest hanging fruit is to go fine tune your embedding model. And we want to keep that in mind at all times. It's a really important tool to keep in our back pocket. And you can always go deeper. If you're already just a master of fine tuning, I get it. And, we have enough for you today, even if you do feel that way about fine tuning. So, further insight into that specific breakout room is when we're down in the weeds talking about test set, validation set, training set. This is the tough part of this class because just because you're an engineer doesn't mean you know any data science and vice versa. This is an engineering class because nobody pays for science and nobody ever has. Nobody's commanded a salary because of science. So we want to make sure that we're focused on the engineering. And if your class or your breakout room is getting down in the weeds of something where most people want to talk about something that you feel is very basic, then we invite you to leverage the one-on-one support to go talk about something more advanced. But we're going to ask that the peer supporters please do serve the majority of the time within each of the journey groups. So thank you for this feedback and keep the specific feedback coming. Amazing. We'll get to this at the end of the day. Shout outs to Mr. Dean and the Whiz. Let's go. Okay, so we've got fine tuning today, and we're going to try to do our best to talk about how to fine tune LLMs. We want to talk about fine tuning and its core applications. We want to talk about parameter efficiency, low rank adaptation, quantization, quantized low rank adaptation. And then also for funsies, we're going to throw in some reasoning today to get you up out to the edge. This is something that is coming onto the scene in real time, and you guys really do need to know about if you're going to take an AM Makerspace course and be certified. So that's why we're putting it in here, and it's right before you have a nice breather week. So we hope that you enjoy the show here. Fine tuning. As we learned in session 1, it's teaching the LLM how to act. We're talking about fine-tuning embeddings last time. We're talking about fine-tuning the chat-style LLMs today. That means the ChatGPT type models. You want to chat with them. The actual ones that everybody knows about. The GPT style. When we fine tune, we want to think about where this fits in the stack. When we do training initially, when we do this pre-training, we have to then take this next word predictor and we have to make it more like what we would expect. And we have to do it in a way that it aligns with what we want to use this thing for. We want these tools to be helpful. We're tool builders, we're tool leveragers. And, this is evolving in real time. It used to be that we wanted them to be helpful. We wanted to be good at following instructions. Now we also kind of want them to, reason, and we want them to think through things step by step, as we saw in prompt engineering. And so, when we think about this, remember, it is supervised. We need an input. We need an output. We can go back to the classics of ML. And again, if you haven't studied this, this is going to be painful for you. But you should study it. But you shouldn't prioritize studying it because, again, it's not always super useful to just be able to build with these things. But it is useful in the long run to understand the foundations. So here we are in supervised fine-tuning land. When we talk about fine-tuning prototypes, generally we're going to grab a commercial off-the-shelf prototype, like a Llama 3 point something. Then we're going to adapt it. We're going to adapt it to a particular behavior, a particular task, or a particular domain. Then often we're going to do some sort of alignment step. Now this could be RLHF, reinforcement learning with human feedback. It could be direct preference optimization. It could be RLAI, feedback, reinforcement learning with AI feedback. All of these are really interesting. We've got lots of content on this. We taught an entire 6-week course on this that some of you took prior to this one. So again, it takes a long time for some of these topics to sink in, but today we're actually going to do both of these things with one of these new methods that came out from DeepSeek, where they're using not RLHF, they're using RL, and they're using not the same optimization scheme as RLHF uses. They're using the GRPO, or Group Relative Policy Optimization scheme. So we're going to actually train our own reasoning model today by pulling a llama model off the shelf. So that means that after you guys do this, you will have done something that basically puts you in the absolute top upper echelon of builders out at the LLM edge. And that's why we want to go and push hard today. So hopefully that's of interest to you guys. Understand that you won't understand everything, and that's okay. There's a lot that goes on at the foundation level where we're looking at loss functions, we're doing training, we're doing fine-tuning, we're doing these optimization schemes. We will continue to explore these at greater depth on our YouTube channel, but they're just not things that are useful to industry today. We want to be able to think at the right layer. So as we are building applications, when we go from prompting to fine-tuning, that's sort of where we're optimizing the input and the output of the LLM. Remember, we talked about this 0 shot is the instruction only, and then there's 1 shot, 2 shot, few shot, 100 shot, 1,000 shot, million shot. When we get to this sort of thousands level, we might want to consider fine-tuning. And as we've seen in recent weeks, it only takes 1,000 samples to train your own reasoning model, to do this, to do that. It's pretty incredible, some of the stuff that's happening right now. In short, we can kind of take this idea of, instead of putting a bunch of tokens into the prompt and examples into the prompt, 1 shot, 2 shot, few shot, 100 shot, 1,000 shot, we can sort of move them into the neurons and rewire the neurons of the LLM that we pull off the shelf. To some end, right? We want to teach the LLM how to act. We want to teach the LLM how to do specific tasks. We want to teach the LLM how to, write summaries or assess sentiment or answer questions. But here, maybe RAG is a better option if you just want to get a quick prototype up and going and you want to avoid the idea of fine-tuning. We can also teach it to learn chain of thought thinking. And this is what we're going to do today. We'll come back to that. You can also just use this to constrain the input and output. So imagine that you say, always respond in a haiku, or I must have an input that is a function call, right? This idea that like my input and output are very well defined. This is so important in product management. It's like, what does the user interface look like? What's the output to the user? The more constrained that I can be with that, the easier it is to build a very cost-effective, very performant model. This is, I think, where that finishing touch piece, when you want to really decrease the cost of it, serving your model to many users every day, as long as they're doing a very specific thing, starts to become quite interesting and compelling from a business perspective. And then finally, you can train these models to kind of understand and learn specific language. This is that domain adaptation idea that we talked about last time. We can do it for chat style models as well. Think about the legal domain, anything with jargon. This works particularly well with code also. We've done this in the past where we get it to respond like it's Gen Z. This is always hilarious. And so, we got these LLMs, but there's a problem. They're very big. And the problem is that if we wanted to actually do a full fine-tuning, quote unquote, full fine-tuning, meaning every single weight, we can't. We just can't do it. We don't have enough compute. We're not compute rich. We're all pretty compute poor if we're in this course. And we also have to then store and deploy all of these different fine-tuned models. And like this full fine-tuning and the storing and deploying of all these different big models, this was identified as a big problem long ago. Well, how have we solved it? Well, that's the story. Part of the way we've solved it is with quantization. And quantization basically allows us to take these weights, these parameters, and these parameters, they're just floating point numbers, right? That's all they are. And if I have sort of a full precision representation of my model, then I'm using 32 bits per floating point number. And the big idea with quantization is that I can sort of take that 32-bit representation of each of the weights and I can make it smaller, and I can hold enough information in my representation to get a good output, to do inference, to get a right, correct answer, but I can do it with much less compute. And this is the big idea. We can kind of say, okay, how many sig figs do I really need? So when we download a model, we want it to be in higher precision generally, because we're pulling it down, and we'll see that in the first breakout room. When we do inference on a model, we want it to be in as low of a precision as possible to get the same output, right? I mean, that makes sense. And then when we do fine tuning of a model, what we want to do is we want to have our calculations be able to be stored in like a higher precision. And then when we're going and we're doing a specific, back propagation calculation, if this word doesn't mean anything to you, it's like a classic word in training LLMs. When we go and we do sort of back propagation flowing through the network to decide on how to update the model weights, we can do that maybe in a smaller bit representation. And so for downloading, we're using 32 bits. For actually loading the model onto the GPU, we're using 4 bits. And this is where, if you don't have like a hardware understanding, there's this layer that you need to sort of bring into the fold now. And then when you do inference, well, it depends on how you load it into the GPU. And when you do fine tuning with something like quantized LoRa, you're going to use quantized 4-bit representations for storage. And then you're going to dequantize back up to a higher bit representation to actually do calculations. And it turns out there are many different ways to quantize model weights. I would recommend following this guy who kind of put out the LoRa and QLoRa stuff. PhD student, I think he's a professor now, crushing it. Tim Detmer is absolutely crushing it. And he put together a library called Bits and Bytes, and that's what we use today. This allows for the flexible use of LoRa adapters, which we'll talk about. But for now, we want to basically load our model up onto a GPU. If you don't have a GPU, you're going to rent one from Colab, and you're going to load the model up onto the GPU. The model we're going to load up is going to be Llama 3.1 8B instruct. And we're going to see that we can actually take the 41 million trainable parameters, and we can see that, like, it's a 8 billion, obviously. So if we look at how many we can actually train, we got this sort of 5 billion, 4.5 billion, but we actually only really need to train a much smaller number. And so this idea of how we load it in and then how we load it on to like the GPU is quite important. So to get set up to be able to fine tune our LLM, which again isn't the embedding model, it's actually the final step, the chat model that allows us to get our better answer. We want to download it first. That's the step we're going to look at. That's what Wiz is going to walk us through right now and show us how to get set up with quantized Llama 3.1 8B instruct. Wiz, over to you.
Okay, so this is gonna be a doozy. This is gonna be we're gonna speed run this process. Now it's not that, so the code is misleading. The code not gonna look so bad. Hopefully you can see my screen. Yes, okay. So the code is not so bad, but there's a lot of stuff going on. Dr. Greg talked about it. Okay, that's good. We're ready. So this is the notebook. There is only a Colab version of this notebook today. You could run this if you had a RTX card, but the support is is potentially a little bit spotty. So we're definitely using Colab. You can use the free tier GPU, so you don't have to, do such a big model. You can just do the regular old free tier. It will be faster if you want to spend credits on it. So if you want to spend compute credits, it'll be faster if you use like an A100 for sure. But you can do this in the T4 free instance, as you see here. T4, let's go. T4, A100, these are just names for GPUs. So T4 is like a smaller GPU than an A100, which is a bigger GPU. Okay, so the notebook is going to eventually walk us through GRPO training with reinforcement learning. We don't got to worry about what that means right now, so we're going to go ahead and we're just going to scoot past that. There's two major things that we're going to discuss before we enter the first breakout room, which is just going to be loading the model, right? But it takes some time. And so that's PEFT, LoRa, and then quantization. Greg's talked to us already about both of these at a high level. We're going to talk a little bit more about technically what's happening behind the scenes. And I'll link a video in the chat if you really want to spend some time with LoRa, where we did like a big walkthrough. But the idea is that we want to do this method called parameter efficient fine-tuning. So we all know, like, these models are big, right? We're always talking about how many billions of parameters they have. So it's like Llama released a 70 billion and a 405 billion parameter model alongside their kind of normalish sized 8 billion parameter model. Well, that's a lot of parameters, right? And every one of those parameters, as Greg outlined, is stored as a number. And so every one of those numbers takes up some number of bytes of memory in our GPU. Now, why do we care about the GPU? We're going to get, too down in the weeds to worry about it, but suffice to say, GPU is faster. That's why we care about training on the GPU, right? The idea is that with PEFT, we can be more efficient in how many parameters that we're going to fine tune. So we're going to go ahead and say, use this method called LoRa, which is going to make us train on a less than 1% of the total number of parameters in the model. So we have an 8 billion parameter model, right? We're going to train on less than 1% of those, and we're going to find that it works staggeringly well. The first thing we need to do is install a bunch of very specific dependencies. This cell is going to take some time to run. Most of these cells in this notebook are going to take some time to run. This is going to be like the theme of the day. As we're going to discover together in the breakout rooms, of course, this is a time-consuming process all around. We're doing like the fastest version of this, and it's still a time-consuming process. Okay, so basically we get all these dependencies so that we can do everything we need to do the notebook. And then we're going to start with Unsloth, and we're going to start with this patch. Okay, so Unsloth is, as you can imagine, is a library for quickening the training process, right? It seeks to unsloth, right? Make faster the training process. So the idea is that with Unsloth, they've done a number of awesome things to make this process, better or faster. One of these things is this patch fast RL. Now, this is like a special, block of code. We're not going to look into it because it's a little bit beyond the scope of our first breakout room. But the idea is that the way we do the generation for RL, which we're going to discuss in the second, half of the walkthrough, is by generating like lots of samples. So we want our LLM, right, to generate like lots of, samples. So we give it one prompt and we're going to get back like 10 to 15 responses, right? So in order for that to be effective, we're going to patch the code that we get from transformers so that it is faster to generate those 10 to 15 samples. So that's what this is doing. It's going to take a little bit of time because it has to rewrite some code, but that's all good. So we use the patch here. Unsloth seeks to make everything fast all the time. This is like the only thing that they do. So we're going to see that's a consistent, part of Unsloth. You'll also see that we have this fast language model. It does what it says in the tin. It's fast, right? It's like a Transformers library, but fast. All right. Next, we're going to talk about loading the model. So there's two phases to loading the model. The first is we're going to download the model weights, and then we're going to shove all of those weights into our GPU. When we download the model weights, as Greg said, they're going to be in full precision. That means they're going to be, every weight's going to be represented by a 32-bit floating point number. So that's called full precision. It is, it's what we train in, right? Good. Okay. So that's big though, right? If every single weight takes 32 bits and we have 8 billion plus parameters in our model, you can imagine many gigabytes, right? So we're going to use this quantization technique in order to reduce the number of gigabytes that we have by reducing the amount of bits we dedicate to representing each parameter in our model. So the way that we're going to do this is through something called QLoRa. QLoRa is just LoRa, which we're going to talk about a little bit in more depth in a second, but quantized. Essentially, they're two separate operations. The Q stands for quantized, and then the LoRa stands for LoRa. We're going to be using a very specific kind of quantization. You might think to yourself, well, why do we care about this quantization thing? Like, why does it matter that the model is like taking up less gigabytes, right? This is mainly advantageous because our GPUs only have so much memory, right? So just like RAM on your computer, the GPU has a certain amount of GPU RAM, and we want to be able to, run big models on as little hardware as possible, right? Or low capacity hardware as possible. And so quantization is what lets us do that. Basically, it is the process by which we can shove big model onto small GPU. We're going to be using something called blockwise k-bit quantization. I'm not going to worry too much about it because it's a little bit dense, but the idea is very straightforward. We're going to take chunks of numbers at a time. We're going to find that those numbers exist in a normal distribution around some mean, and then we're going to use a very special data format called NF4 to represent those numbers as where they exist on that normal distribution, right? So the entire point of this is to compress the way that we represent this information. So we're going to go from, again, this 32-bit number all the way down to NF4, which is extraordinarily small, in terms of size. It's in fact 4 bits. So we go from 32 to 4. So that's a big reduction, right? And we already talked about this parameter efficient fine-tuning thing, which is going to take us from 100% to less than 1%. So you can see that combining these things together gets us from the realm of very big all the way down to able to run it on the free instance of Colab. There's lots of words that you can read about quantization in the notebook, as well as, of course, we recommend reading the papers. But the idea is straightforwardly that we take the 32-bit number and then we represent it with only 4 bits, which is not very many bits. Go team. Now we're going to talk a little bit about LoRa. The big thing with LoRa is that we can just use a trick of math, right, to get from this 100% of the parameters we need to train all the way down to less than 1% of the parameters that we need to train. And this trick of math is that the weight matrix, this is we're always talking about matrix multiplication when we're talking about language models, right? Or transformer models, where we're always multiplying these matrices together. That's like the whole thing. That's all we do, right? Well, these matrices, it turns out, have what's called intrinsically low rank. All that means is that we don't need all of the numbers in the matrix in order to represent that matrix. So we can just get rid of a bunch of numbers. And one way to do this, the way that LoRa uses, is to create 2 smaller matrices that, when multiplied together, are the same size as the original matrix, but each of them is massively reduced in size. So what we do is we have this hyperparameter, right, which is like it's a parameter that we set while we're thinking about how to train things and things like that, right? So, but the idea is we have this concept of a rank. All that means is like how big is one side of our LoRa matrix, right? So let's say we start with an original matrix, n by n. What we're going to do is we're going to convert that into a matrix of r by n by r. So that when we multiply them together, they result in a matrix that's back to n by n. If this is going fast and you're like, what the heck is this guy talking about? Again, we have tons of resources for you to dive deep in exactly what's going on here. But the basic idea is that the matrices that we have in our models are full of redundant, collinear information, which we don't need, don't care about, and can just do away with by using this LoRa method, where we instead use these very small submatrices that multiply back to be the same size as the original matrix, so that we don't run into issues with our model. So there's a great paper on this, tons of stuff. LoRa's been around for a while. It's just something you do. There you go, LoRa. So the way that this works in code, again, very straightforward, right? We're basically going to just use our fast language model from pre-trained, from unsloth. We're going to point to the model name. We're going to give it a max sequence length, which is determined by us. This max sequence length is what you might have heard referred to as like a context window, right? So you'll see that this context is very small, and this is, again, so we can fit this easily in our very small GPU. If you use a bigger GPU, you can play with these numbers. You can make them bigger, do some experimentation. I definitely recommend doing that if that sounds like fun. But if you don't, these are going to make sure that it works out of the box. We're also going to set our LoRa rank. This is just saying how small do we want to make those constituent matrices that multiply into the big one. This can be as low as 1, right? So we see here that it can be as low as 1 without like massively reducing the performance, and then it can be as high as the original matrix size. Though at that point it would not be useful. We have load in 4-bit. This is the whole thing that does the quantization from the code side, right? This is all we do. We just use load in 4-bit equals true. Thanks, Unsloth, Tim Detmers, all those that came before. In order to set our matrix rank, we just pass it in. Again, the code for this couldn't be easier. The concepts maybe a little deep, but the actual code very straightforward. GPU memory utilization. Okay, so GPU memory utilization is basically just saying how much of the GPU's memory should we utilize, where a number close to 1 is, you can think of it as a percentage, right? So this is 60% of the GPU that's being utilized. We want to set it a little bit low. We want to have some headroom, some memory left over in our GPU, so that we can fit in the sentences, the context, the thing, the prompt, and the generations, right? So that's why it's at 60%. And then we do this get PEFT model thing. All this is doing is it's applying that LoRa that we saw to specific targeted layers of our model. So we're not going to go deep into this. Come to office hours if you do. Watch the events that we've done on this if you want to go deep on it. But the idea is that LoRa is better if we apply it to specific layers, depending on what kind of training we're doing. So this is why we do this. That's it. All right. This is going to take some time, and you're going to see a lot of stuff going on. It's mostly self-explanatory. It just takes a long time to download the full model, which is big, right? And then, of course, we're going to be able to look at the actual layers of the model, and there's going to be some questions that you can answer about the model while you wait for it to load in your breakout rooms. But that's the idea. Again, the concepts, there's a lot. There's a lot going on here, but the code, man, I mean, they made it as easy as possible. Okay, with that, I'm going to send you guys back to Greg, who's going to get us into the breakout rooms.
All right. Thank you, Wiz. Yeah. All right. So guys, I just want to make another quick reminder here that as we head into this first breakout room, this is just about loading the model in. And obviously, just to load the model, there's a lot of stuff that we just had to go over. The reason that we're going over it so quickly is because it's no longer important to industry like it used to be. When industry says they want to hire people for AI, they don't mean this. This is sort of table stakes, but it's not going to make or break your ability to do things today. Although if you're really doing everything, you're going to want to learn all of this stuff eventually. These are trailheads for you, and we understand that it's a whole heck of a lot. And I personally have been trying to wrap my head around all of this stuff for years and years now, and it's just a lot. It continues to grow into more and more. So where we really want to go end to end in this course, we can't make this course be an entire year long course, and we have to focus on what matters to industry. And fine tuning of LLMs is just not it. That's the reality of the situation. Although, if you can fine tune a Llama 3.1b 8, a Llama 3.18b instruct off the shelf to do reasoning like DeepSeek R1, that's going to perk up the ears of anybody that you're talking to, whether it's an investor or it's a person interviewing you. So that's why we're pushing so hard today. And we hope with that you guys are able to dig into some of these trailheads and have some fun with your group. Loading in your first model onto the GPU, 15 minutes, and we'll see you back just before 8 o'clock p.m. Eastern. Thanks, everybody. See you soon.
It looks like it is.
Yeah,
I
okay.
just didn't hear it.
Okay. Update. Okay.
You're live.
Yeah. Can we record a local one too, just in case?
Yes.
Yeah, okay. Let's also do that. Okay. And we're back from breakout rooms, and we are on to the next part of our discussion before we get into actually fine-tuning our own reasoning model. And, Wiz talked a little bit about this in the notebook, but the idea is we need to understand that we've got these large models, we're pulling them down. We want to do as much with the compute as we possibly can. And when we fine tune, we want to never be doing full fine tuning. We want to be doing fine tuning in a way that is efficient with the parameters that we have. And there are many methods to do parameter efficient fine tuning, or PEFT, many methods. But the one method that you should definitely know is LoRa. And LoRa stands for low rank adaptation. We've talked about this a little bit. Greatly reducing the number of trainable parameters. That's one big piece of this. So the idea of this intrinsic rank is that most things don't matter. Some things really do matter. We want to focus on the things that really do matter. It's like which dimensions, if you have a classic ML background, which features are the most important. We can think of it as that. And which of those should I be training and retraining? And there's all this sort of background matrix algebra you can get into, and all this stuff that is quite interesting. The one thing that LoRa adapters do is they actually leverage some of this. So if you're into those math details, go look at it. If you're not, you don't really need to, but it's a pluggable adapter. Basically, you can think of it as you're just going to plug it right into the transformer. And we're gonna freeze all the model weights of the transformer. And then we're gonna have this pluggable adapter that we just slap on there. We say train this. So it's almost this empty cell we're putting in there. And this is the big idea behind LoRa. If we use pluggable adapters, we can have many specific task adapters. And the big useful thing here is that we can make these adapters focused on saving us money while getting the same performance. I think this is going to be the key, or as we saw in fine-tuning embeddings, giving us privacy for our data and giving us the same level of performance. Okay, so this is one of the big things. It allows us to do this open source thing, and allows us to decide on which adapter we're using at inference time. And this is very cool because we're not locked in to any given adapter. This is from June 2024, and this is from Apple. and they were talking about their new release. And LoRa is good because we can do cool stuff faster, more efficiently. We can do more stuff on device. You'll see this more on edge device, et cetera, et cetera. But models are always getting bigger. So there's LoRa, and you should understand it. And you know, when we think about fine tuning, it's teaching the LM how to act. We're modifying behavior. When we think about PEFT, we're doing the fine tuning with fewer parameters. We're trying to be efficient. When we do low rank adaptation, we're doing fine tuning with these matrices. And when we then kind of put all this together, we're doing modification of behavior of LLMs by updating as few of the parameters as we can using this factorized matrix pluggable adapter approach called LoRa. But actually, the follow-on work that has become the standard now is called quantized LoRa or Q-LoRa. And this one is like going to take the quantized version, and it's going to use also the dequantized set of model weights to do computation. Because there was all this research done, and they said 32-bit is overkill, 16-bit is really good, but we don't need 16-bit for everything. We just need it for actually doing calculations. If you remember sig figs, that should be sort of a clear intuition for you there. And so we layer in this quantization. We layer in this 16-bit computation dequantization during the Q-LoRa process instead of just straight up using 4-bit all the way. So quantization is representing high precision with low precision. So if we do PEFT Q-LoRa, we're modifying the behavior, fewer quantized parameters using these factorized matrices. The thing you should take away is basically you'll see it everywhere. You'll even see it in state-of-the-art, you know, companies that are doing really, really cool things to accelerate training and to accelerate fine-tuning, like Unsloth. And they're doing this, and that's what they did to set us up for today. So what we want to do is we want to basically train a reasoning model. The idea of reasoning, we've talked about this in many recent events. We haven't talked about it much in this class, but it's based on these chains of thought. And chains of thought, as we talked about, are these things we need to do to solve word problems, like from back in school. If you look at what people are saying about some of the latest reasoning models, like DeepSeek R1, it's just the next step. Indeed, it is just the next step. And I want to just, you know, chat for a moment here, Wiz, with you about this. We're thinking before we answer, okay? That's what we're doing. And so however we get to the point where we trained this model, that's what it's all about, right? And so the question that people should probably be asking is, when do I need a model that thinks before it answers? And when is an answer that just kind of pops out okay?
Yeah. So like the way I would think about it, right, is it reasoning is a tool we should reach for when the task is particularly complex or like multifaceted. So if it's like one shot, right, from context to response, we really don't need a reasoning model. So for like most RAG pipelines, right, or what we really need is something to be able to take knowledge that is given and produce a response based on that knowledge. Reasoning models are not. There's no point, right? When we're talking about more complex tasks like task decomposition, so taking a task and turning it into many small tasks, or we're talking about something that requires planning, or any of these like what we would consider to be system two, things, which means like the slow, deliberate thought. You got to think it out. You got to really when you're making a plan, you can't just like just spitfire, boom, the plan is done. You've got to think about each step, et cetera, et cetera. That's where reasoning models shine. They're incredible. They're amazing. But for anything where it's like one shot from input to output, like don't use reasoning models. In fact, they're worse at those tasks. As well, right now, today, February 13th, 2025, they're terrible at function calling and structured outputs. So when we want to do function calling or we want to have structured outputs, the models, especially open source models, they're really bad, to the point of not being particularly useful at those tasks.
Yeah.
So those are things that do work in your agentic flow, right? The thing that actually calls the tool, right? The code agent, the tool node, that should not be powered by your reasoning models. That should be a worker LLM, a good solid llama something. Yeah.
A good
So
worker.
Dirk says in chat, all open source models suck at tool calling. No. All open source reasoning models suck at tool calling. Llama 70B is a tool caller's dream. But the reasoning models are not yet there. They will be in time, but not on February 13th, 2025.
Yeah. Okay. So, I think the big idea here is like you don't hire a PhD scientist to take orders, that the robot can take, right? That's what we want to think about with reasoning models. When do we need this kind of additional, because it costs money, it costs compute, right? And there's this thesis that the companies with the most money and the most compute that can spend the most time thinking about the hardest problems will be the most successful, right? It's like the classic Matthew principle, right, at play here. It's like, so what in your org or what you're trying to do might benefit from this is the question you should ask. And the thing that's interesting is we have thinking tokens. Wiz will talk about those. And then we have this idea that if we taught it math and we taught it reasoning, and we taught it how to do math and code, then it learned how to get the chains of thought for math and code, and then it can basically go apply these chains of thought to other domains. Like it became a solid A student, nerdy engineer, and then it's like, oh, okay, how can I take these patterns and these tools that I learned and apply them elsewhere? And it does this through reinforcement learning, through like play, right, Wiz? Through this sort of like classic RL approach, where we're not saying you must have the same output as what the human said. Where when we do something like RLHF, we say, no, you must align with what the human said. This one's sort of learning something kind of fundamental about the way to think through problems. And that's very exciting. And that's why we forced it in here, guys, because it's something you should know about. And it's something you should think about as you're building your applications. Does it need reasoning? Does it not need reasoning? All the fine-tuning deets and all this other stuff, it's like that maybe doesn't belong so much in our story anymore, because it's more of a table stakes. But for now, we want to take a look at how to actually create this open source, see what the performance is like. Wiz is going to walk you through some of the details along the way. You likely won't understand all of them, but it should be a lot of fun to fall down some rabbit holes today. And this is not on the midterm. Wiz, over to you.
Okay. So we're going to talk about a lot quickly. The first thing we're going to talk about is that there's a thing that's happening behind the scenes that we're going to spend almost no time on today, which is the actual fine-tuning or the wiggling of the weights, right, in the model to make it better at our task. So we're going to skip forward past that a little bit, just to make sure that we're all in the same space. Again, this is happening. We have tons of content if you want to go super deep on it. Welcome to office hours if you want to go hard on what's happening. But the idea is that like the libraries we're using are going to take care of that for us, and they're going to do it in a way that is most efficient and effective. The first thing we need to think about all the time with any training job, fine-tuning, it doesn't matter, is data. Now, the data we're going to use today is an interesting kind of data because, again, we're not teaching the model how to think. We're not teaching the model how it should go through this. Instead, what we're doing is we're just giving it the beginning and the end, right? We're giving it the start and the finish, and we're going to allow the model to explore how to get there most effectively. This is what separates this kind of training from traditional supervised fine tuning, whereby we're very prescriptive. We tell the model, this is how you should think, and I'm going to give you rewards if you think that way, and I'm going to I'm going to penalize you if you don't. So the data that we're going to use is from the GSM 8K data set. GSM 8K is grade school math, and there's 8,000 samples. So there you go, GSM 8K. The idea is that they're grade school math problems, and we're going to learn how to get very good at those. It's a classic benchmark for models. It involves, or it benefits from reasoning. We have some stuff that's happening here. Now, we have been using the API to interact with our models for entirely so far, right? We've always had this idea of like a system prompt or the user prompt, right? Or the assistant prompt. This is kind of how that happens behind the scenes. So there's actual formatted blocks. The LLM only has one input, right? It's got one context that it looks at, and this is what's happening kind of behind the scenes, is that there's this formatted prompt situation. We also have this XML thing. We're not going to worry too much about that. XML is just a way that we're able to tell that the model is producing things in a format that we're like stoked about. Okay. We have our extract XML answer. This is going to, unsurprisingly, rip the answer out of these answer XML tags. And then we're going to have extract the hash answer. This is going to be if the answer is returned to us on the kind of hash. So this is one of the ways that we can format our prompts. If you've used something like ChatGPT before, you might have used like this markdown formatting to interact with it. This is what we're seeing here. And then this is just getting the GSM 8K questions. We're just loading them up and we're shoving them into this format. So we're going to look at the data set and see how that winds up looking. We wind up with a question. Natalia sold clips to 48 of her friends in April, and then she sold half as many clips in May. How many clips did Natalia sell altogether in April and May? A classic grade school math question. Easy peasy. There you go. What we're going to do is we're going to, feed that as a prompt. And then we have the answer, which is 72. Now this response is correct as verified by some by the people creating the data set. So what we have is we have word problems that have some number as the answer, right? So that's our inputs, and then this is our outputs. So we're gonna skip past this dense diagram for a second, and we're gonna look at a reward function. So one of the best parts of the method we're using today, which is called Greg's talked about GRPO, Group Relative Policy Optimization, is that we have a group of metrics, and we care about how each of those metrics does relative to the group, right? So instead of, say, having like a metric, that we want to do well on, we have like, in this case, 5 metrics. And what we're going to do is we're going to see how a response does on all of those metrics, right? We're going to take a single response and we're going to collect the average score of each of these 5 metrics. And then we're going to do that for each prompt in our batch of prompts, which is going to be 10 to 15 of each time we do a step of training. So what this means essentially is that we're going to wind up with an average, right? And then we're going to have some prompt or some responses that are better than the average and some responses that are worse than the average. And the thing that group policy optimization, group relative policy optimization is taking advantage of is this idea that the ones that do better than average are the ones we're going to give rewards to, and the ones that do worse than average are the ones we're going to penalize. So it doesn't require us to have a mechanism by which to establish a baseline like good response, right? We just rely on wisdom of the crowd. And this is what makes this approach so good, especially when compared to the way we used to do things, right? Which required this whole other model called a critic, right? And it was like, so you were running two models, et cetera, right? No bueno, no good. What this does is it say, hey, I'm going to generate, 15 responses to this prompt, right? So let's say for example, right, we have this prompt. I'm going to generate 15 responses, and some of them, right, are going to score, well on a correctness reward function, good on int reward function, maybe not as good as a strict format, et cetera, but we can take the average of all of their scores, and then we can say, okay, these ones did better than average. Those prompts are more, you should produce outputs that are more like those prompts that scored above average in that batch. So what do the reward functions actually do, right? Because this is different to like normal loss in a machine learning model. Well, all the reward functions do is they just like give a score based on something. In this case, we're going to give a score based on if the model got the answer correct or not, right? So correctness is one of the things we score. Then we have, int reward function. This is making sure that it's in int. So it's just a number, right? You get points if you produce a number. Then we have points if you follow this strict reasoning template that we've set up. We have a soft reasoning template, where you still get points if you were close. And then we have, do we have the correct number of XML tags, or the expected number of XML tags in our response, which we will give points for. So essentially, we have 5 different ways we can give points to a model's response, and we take the average of those scores for each of the prompts in the, say, 15 total responses. We use the average score to set the threshold, and then we give plus points to the ones that are above and minus points to the ones that are below. That's it. That's the whole thing. I mean, there's no more to it, right? Like this is the reason that we're using this approach, this reinforcement learning approach, right? Is that it allows us to have the model explore options, right? So there's 2 phases to the reinforcement learning approach. We have the explore and then the exploit phase. What we want to do is we want to let the model explore. We want to let it learn on its own, right? Figure out the best way for it to learn how to get to the response, and then we want to find a way that we can exploit that. This method finds a nice little balance between the 2 of them. Okay, so that's a lot of stuff on GRPO. So how do we implement it, though? You knew it was going to be easy. It's just a bunch of parameters, right? So we have our training arguments. These are all just the normal training arguments. There's no special GRPO training arguments that we're using. These are just the normal ones. We have our learning rate. We have some betas for our gradient. We have some weight decay penalty. We have some warm-up ratio. All of these words mean things. We can dive deep into them in office hours or in the supplementary material that we have. But the idea is this is kind of stock hyperparameters for training a model, right? The only thing that's different is that we're using a smaller learning rate than we would typically. We want the model to learn slower, is the idea. Okay, so that's what it's doing. That's all it's doing. Perfect. You got to answer some questions by reading the documentation classic, and then we do our trainer. And our trainer just takes our model, our tokenizer, our group of reward functions, and then those args and a data set, and then we call .train, and then we be training. And we train for a long time. This is going to take a long time. You are not going to be able to complete this training in the breakout session unless you massively reduce the number of steps that you do in training. In order to get to a good reasoning model, though, you must train for a little while. So we'll look at the line go up. So you'll see that it takes a while for us to get into the range of decent scores. The maximum score you can achieve is 2.5. There's weird rounding issues, but the max score you can get is 2.5. And you see that it takes a long time. So this is 200 steps, right, to get to where it levels off. So you're not going to be able to recreate this graph in the breakout room, right? But you'll be able to start the process. You'll be able to start the training in the breakout rooms. But you'll notice that it takes a while for the model to kind of plunder around, right, in order to get to a semi-consistent working strategy. And this is the whole idea of this GRPO, or reinforcement learning strategy. It is efficient, but it takes a while, right? Because we're letting the model play its way to reasoning. The other thing you're going to notice is that a bigger model is going to be able to do this even better, right? So if we use, say, a 70 billion parameter model, if you have access to that kind of hardware, it's going to be able to reason even better at the end of it, right? And it's going to take it less time to get kind of ramped up into that reasoning. This is one of the things we've discovered about these reasoning models. So why does this matter? Why do we care? Is it better after the end of this process if you really just let her rip? Yes. So we have, for instance, this is our stock output. The question is calculate pi. You can see here that it does not even calculate pi. It runs out of tokens before it gets there. But you can see with our GRPO trained model that not only do we calculate pi, but we calculate the first 1,000 digits of pi. I don't think this is literally true, but we have 102 correct digits of pi in a row from our reasoning model compared to 0 correct digits of pi with our non-reasoning model. You can also see that the idea of thinking through in steps is being baked into the model. The answer output is what we would expect it to be. Very good model. Good job. That's what we're doing in the breakouts. Again, we're going to start the training in the breakouts. We're going to finish the training once class is over. I'll pass you back to Greg to get us into those breakouts so we can crush it.
All right. Thank you, Wiz. And it's time for a nice, luxurious breakout for you guys. Enjoy this one. When you come back, I'm going to go ahead and tell you a little bit about the midterm. It's going to be something you can review over the next 5 days or so. But again, I want you guys thinking about problem, audience, solution over the weekend. We'll come back on Tuesday, and then we will go ahead and properly assign the midterm after you turn in the homework from this week. So we're going to have actually 25 minutes up on the clock here for this last breakout room. We'll come back. We'll close it out. Enjoy. We'll see you guys soon. Okay, everybody. Thank you for filling out your feedback and for sticking around a couple of minutes. I will owe it back to you. Next week, we've got a really chill week. Join us to keep building, chipping, and sharing. Join us to talk about chains of thought in latent space. Join Vincent's deep dives to go deeper on some of these prerequisites. Join anybody in any office hours. And I want to show you what's going on with this midterm. I'm going to drop it into the chat. It's also on the homepage. And what you'll notice if you go through this is it's going to be due a week from next Tuesday. And, welcome to the middle, blah, blah, blah. You know enough already. When we ask questions about how and why to use patterns, it's quite difficult. So all this is preamble. We're here and there's a couple tasks. Each task has a deliverable. The first thing is you want to define which problem you're going to solve, who your audience actually is. There's some hints here. There's a specific task. There's some deliverables. Then you're going to propose a solution, because for any given problem, there are many possible solutions. You're going to have some specific deliverables here. Then you're going to decide, what data do I need for this? At least we need you to get a PDF up in here. Okay, just grab you a PDF so you can do some RAG and some agents. Okay. And at least use like a Tavily or a Google SERP API, Google search through SERP. Okay, at least we're going to need you to do that. There's lots of stuff you could also do. And then you're going to build a quick end-to-end prototype. We know how to do this. We did this in session 3. Then you're going to create a golden test data set, so you can do some evaluation on your RAG. And this is also going to lead to fine-tuning some embeddings and assessing performance. So what we want to do ultimately is we're going to force you to build out your portfolio in a way that you're going to be proud of and is going to be useful to you. And it's going to be super useful for you getting prepped for demo day and whatever you want to go do thereafter. I want to be specific here. We're going to need you to have a GitHub repo that has a 5-minute or less Loom video that is a live demo of your application. It is not a full walkthrough of everything. We don't need that. We just need a quick 5-minute demo and a written document in that repo addressing each of these questions and deliverables, and then any code. A public, or if you're doing something private, it has to be private for your company. It has to be private because you want to, bring it to market. We can work with you on that. Jacob or whoever's grading it will need access. We can work with you on that, no problem. But generally a public link, generally a Hugging Face link. If you want to build it somewhere else, you want to get more sophisticated, that's great. And then a public link to your fine-tuned embedding model likely on Hugging Face, okay? That's what we want to see. We want to see that you've been playing along. We want to see that you've been doing the work. We want to see that you can build, ship, and share the things you need to be successful in the market today. And you'll notice fine-tuning an LLM is not on here because we do not believe it is required for you to be successful in the market today. So go ahead and shoot us questions in cohort questions. Tag me, please, if you have specific questions for me, and I'm happy to answer them as best I can. We will go into much more depth on what's necessary next Tuesday, and we'll spend the whole week on this. We'll also have some fun on Thursday. We're gonna give you guys some time to hack together, to sort of meet with other people, to sort of think about your demo day groups. Just because you do a midterm project doesn't mean that's your demo day project. It just means you have skin in the game to join another group, to get certified, to show that you're going to be a legend in the community and outside within your network as well. Okay, so we hope that this is something that's going to be useful to you. Join office hours if you need help ideating, and thank you for your extra time today. I sincerely appreciate it, and I'll do my very best not to steal it again. Thank you so much, and we hope to see you guys again real soon in office hours, on Discord, and on LinkedIn. Don't forget to build, ship, and share. DP, Ben, all you guys, keep it rolling. It's looking good. All right, thanks for joining us. Have a great weekend. Keep it chill. We'll see you next Tuesday or midterm week. Bye, guys.
Bye, everyone. We've got a couple cues in the chat, Greg, if you want to just quickly take a look.
You've got to do the fine tuning of the embedding model. We want to see that you did the fine tuning. Nilay. Fine tuning an LLM chat model is not needed, because fine tuning an embedding model is quite a useful thing to have in your tool belt. We want to make sure that you have it. Okay, that's good. Thanks, guys.
Bye, everyone. Have a good weekend.
Have a great weekend. You made it halfway. Let's go. Woo! 5, 10. Later, guys.